So yes, let's start discussing the discrete Fourier transform for now. Fine. So first of all, what is a wave? I would like to start with the concept of a wave. Then you will slowly understand why we need discrete Fourier transform in the first place. Can you tell me what is a wave? Like we'll start discussing Fourier transform, but Fourier transform. But I would like to ask, what is a wave? Wave means yes, it's something, but it's not a bubble gum, not a chewing gum wave. Something different than you eat. What is wave? Anyone? Just randomly you can say it. Doesn't have to be correct. Okay. Okay. So one good example is if you have a pond, and suppose this is the pond around. Yeah, it cannot be square like this, but yes, just think. And this is the water, like very still. And what one does is there are trees here, okay, and there is a person sitting on the tree, okay, and he throws a water. Sorry, he throws a stone, okay. He throws a stone, okay, and that stone may be blue color, no, red color stone. Yes. The red color stone is approaching and it hit the water surface, okay. So what do you think? What kind of behavior you will see? Yes, that everyone knows because everyone has seen it. Okay. So these circular patterns will be developed. Okay. And it will be spreading throughout the entire water surface as much as it wants to go, like disperse as much as it wants to disperse away from the point of impact, isn't it? And at one point it dies. At one point the amplitude dies off. Yes. So therefore, this is one example of a circular wave. Circular wave, we also call it like some many projects students are working on this, like to mathematically model these things, okay, and these are technically known as target waves. Fine. And in your heart, like if you see, where is the heart here, no? So yeah, the size of this hand, like the palm is the size of your heart. Yes. So the scientists have found that many people they experience cardiac arrhythmia, right? Cardiac arrest. So what is the reason behind this? And when people were having cardiac arrhythmia, they were checking it why it happened, and they did a 3D heat diagram, and they came to know that after getting those data and using the data visualization technique, like you assign the values to each color. If it is too intense, if it is oscillating very highly, put that red color, that area to be red color. If it is oscillating less, put that green color. And they saw a pattern. Actually, what kind of pattern they saw is this. What kind of wave is this? Anyone? It's a spiral wave. Okay, because it is spiraling. It's a spiral wave. So spiral waves are something which is causing cardiac arrest. Spiral wave is something which is causing cardiac arrest. So therefore, people are now focused on like how we can minimize the occurrence of the heart disease or the cardiac arrest. Okay. So this is how to control these spiral waves. Control the occurrence of spiral waves is one of the most interesting problems till now in literature. Even in brain activities like neuroscience, you know, neurons are collected in a very large network. Millions of neurons are connected. Okay, I think you remember my first day slide. I think I talked about this a bit. Okay, so there also you see these spiral waves. People with repeating patterns, like who are having this, cognitive disorders, mental disorders, they behave in a certain way. Okay, this happens due to this kind of wave. Okay, this kind of wave persisting in their brain. Okay, so just how you can shift these regimes, these we call regimes, these patterns are the regimes. How can you shift these regimes? You have to apply some shocks, you have to apply some external disturbances to make them move away from that disturbance, okay, to move away from those waves. Okay, so the waves are very much important. Okay, but anyway, the waves are something finally is data. What is a wave? Finally they are of something known as a data. But you visualize it and you see it as a wave, but wave is before the wave, like in backside of the wave, all are data. Okay, everything is data. Fine. So wave is something like it varies both ways. Wave vary over time? Do you think? Does wave vary with time? Or no? Yes. Does wave vary in space? Does wave vary in space? I told you two things. Wave varying with space, is it yes or no? Or wave varying with time, yes or no? Which one? Time. How many of you also say that space can also be wave varying with space? Wave varying with space. Yes. So wave can vary both ways. Wave can vary both in time and space. Okay. If wave varies with time, wave varying with time is something known as a temporal patterns. Like temporal way it varies. If it varies with space, then it is spatial. Okay. It is spatial. Okay. So therefore, you can know why there are some courses in geoinformatics named as geospatial. Some courses names, there are something known as geospatial because they are studying in different parts of India. Okay, the locations, different parts of India, that is different spaces. So therefore, it is spatial. If it is time varying, it will be temporal. Okay. So therefore, if you have heard of these guys I told you just now, these are something known as spatio-temporal patterns. Okay, spatio-temporal patterns because they vary both in space as well as in time. Okay, how they are varying both in space and time? You are not getting any intuition, right? Varying with time, you are getting intuition, but varying with space, you are not getting intuition, is it? So now we'll see a Python code which does that. Okay, but before that, let us just complete some of the basic understanding. So many of your waves are difficult to see, such as like sound waves. This wave you just able to see, but sound waves I'm speaking, and you know that the sound waves are going to you and vibrating in your eardrum, therefore you are able to hear, but you are not able to see those sound waves. Okay. Anyway, so and even like earthquakes, yeah, and there are radio waves inside a microwave you can't see. Hmm? So wave is a disturbance. Okay, wave. What is a wave? Finally, the simple definition for that will be like it's a disturbance that travels through space and matter also. Okay. Okay. So let us see this example so that it will be easier for you. Let us try to model a wave. Okay. So wave is a kind of a mathematical function. So since I told you it can vary with space and time, we can write waves as a mathematical function like f is a mathematical function which denotes the wave. And I told you it depends on space and time. So I can write it in space x comma time t. Okay, fine with you? So what is this giving us fxt? So it gives us the status of the wave, that is the status of the wave at time at location x, and time t. Okay. So we will try to see how this changes over both space and time. So for that, I think what we can do is just plot a simple sine wave. Okay, simple sine wave. I will show you how they vary with the space and time. So yes. So here you can see. Can you see last benches? No. You can see. Is it Chaco? Okay. So yeah, maybe here I can zoom in. Yeah. Okay, let us see. So here I'm plotting, like you can see x is varying from 0 to 20 in 200 steps, 201 steps. And what I'm plotting at those selected values of x, I'm just plotting sine of that quantities. Okay. So for what I'm doing in between 0 and 20, I'm taking 200 set of 200 points. And for those 200 points, what I do? I compute the sine of those points. Okay. And that is stored as y, and I'm just plotting x comma y. Yes. So this will give you something like sine looking. Oh no, no. Yeah. It will give you something like sine looking function. Yes, here you can see that. On your y-axis is nothing but the amplitude we say of the wave, and x-axis is the location of the wave. So you can see here in this example that the wave is varying with respect to the space. So this is known as the spatial variation, because if you see the x-axis, the wave is continuously growing, isn't it? It changes with x. Is the wave constant with x? No, it changes with x as compared to like sine wave. Yes. Now I will give you an example how this sine wave changes with time also. Now you looked only into the space. Now let us see the time factor. Okay. What I do here, just go through this code, like just wonder, like have a look into this code and think what this code is doing. I'll give you 2 minutes. Mm-hmm. Anyone? What it is happening? Hmm. For each second, what you are trying to visualize? You plot the wave. Okay. And for each time instant, you are plotting the wave. Yeah. And that how you take care of that? You take care of that using the for loop. Okay. You see how I'm taking the for loop for t in times. And times is an array, isn't it? Times is an array, and time will be taken from 0 to 4. That is 5 minus 1. Yes. 0 to 4 it will go. Hmm? So for t equal to 0, and does the plot will vary with time? Do you think? Do you think the plot will vary with time? Why? Yes, sine x plus t is there. So every time in your for loop, if t is changing, then sine x plus t will also change its value. It won't be the same. Like sine x plus 1 won't be the same as sine x. What will happen to that quantity? It will be shifted. Sine x is this quantity. If you add x plus 1, all the x quantities are shifted by 1. So it is just like you shift the graph like this, just like shifting an image to the right or left. Okay. So therefore you'll see the snapshots. You'll see the snapshots for 4, like 0, t equal to 0 to t equal to 4. And I'm doing something more important here also. What I'm doing to make you understand that we are varying the like with time, actually the location and the wave changes with both space and time. What I'm doing is I did a clever trick. What I do is I mark a point that is x25. Okay. That x25 will be the same location, right? It will be the same location, but the value might change of that location. Yes. So I plot that with a red dot. You can see this in here. Plot x25, y25 with a red circle. Yes. So that red circle, keep monitoring that red circle. Yes. So you can see that here. Yeah. Yes. For t equal to 0, you can see that uh, this 2.5 is constant, isn't it? The red dot is present at x equals to 2.5, but the y coordinate for that is changing. The y coordinate for that is changing. Okay. And due to that also, you see that yes, it varies with space and also varies with time also. Now can you understand why I told that the wave can vary both in space and time? Okay. So this is a good example where you can understand why a wave varies with time. Okay. Is it clear for to everyone? Or? Like just look into t equal to 1 second. T equal to 1 second, this guy was something non-zero. Let's check the y value. It is something non-zero. But when t equals to 2, this guy got 0. Sorry, -1. And here again in between -1 and 0. but all above terms times this guy was positive. So it is changing with time. Got the idea, no? Anyone, any issues? Or we move forward? We'll move forward. Hmm? So this one is done. I think any other example is there, is it? No. We'll see more later. Let us be back. Okay. So a wave has some characteristics. A wave has some characteristics. What are the characteristics of the wave? Any ideas? Now you just look into a wave. You just looked into a sine wave. What other characteristics does that wave have or possess? Any ideas? Yeah, she said amplitude, you said period, and anyone else? Ah, yeah, wavelength. Anyone else missing something? Yes. So a whole class told that whole thing. So amplitude, period, wavelength, frequency. Okay, how you can incorporate all these characteristics into the wave? Now that is the question. How you think we can incorporate all these quantities now inside the wave and write it as a mathematical function so that we can take advantage of that wave? You will understand why I started discussing about wave before talking about Fourier transform. This is the last phase. So where you will deal with some part of physics, but after that we are good to go. Hmm? Any ideas? How you can implement? How you can implement the period, the amplitude, the frequency, and all? Take sine as a special example and think how the amplitude is coming there. See, sine is a wave. So think that and think how you got a period there, how you got amplitude there, how you got frequency there. Treat that as a special example and let me know. Hmm? Hmm? Yeah, I won't tell unless you tell. Yeah, you have to say in terms of sine. Hmm. No, that is its amplitude. Hmm? And it repeats again after like 0 to 2 pi again after 2 pi to 4 pi, so it's periodic. Okay, and it has a certain frequency also. Okay, so how in that sine you get all these quantities I'm asking? Hmm? I'll wait for your answer. I want you to think. I want your brain to get exercise a bit. Sine is a function. Everything should be there. Then what is stopping you to define all this in the inside sine? No, no, that is a Taylor series. That is no, that's we don't want. Okay, so I'll tell you two things here, which is quite important. Let us begin with that. So, what is the amplitude? Like, let us draw a wave. I think I should have drawn it before in the class. Else, like, no worries. Suppose you have this. You have a wave where you have this amplitude versus time plot. Okay, amplitude versus time, which you just saw, like in the sine case. It was going like this, isn't it? Yes. It was a sine wave, and basically sine wave is just a mathematical function, but actually in real life you will get data points. Actually in real life you will get data points. That means these data points will be given to you, and these are known as like sampling. Okay, these data points will be given to you, you just join them together. The more sample points you take, the more accurate it will be. That is known already. Okay, so like this you join and come to know that this is sine wave. Okay, now in this plot, in this amplitude versus time plot, can you see that this guy went up, came down, and again went up? So can you tell me what should be the period here? The period should be, take this guy for example, If this guy repeats again, if you consider that x, that time distance, that will be the period. So when it repeats again, can you tell me this side? No, it can't be this because it is on negative side. So can you tell me what should be this? This is the period, isn't it? This value repeated in at this point again. So that is the difference and that is the period. Okay, fine. What is the amplitude in this case? Yes, this guy will be the amplitude. This is the amplitude. Similarly, this is also the amplitude. Okay, fine, fine. Now this is the amplitude versus time plot. We can have a similar plot also. We can have a plot of amplitude versus location. What do you think? Can we have? Hmm? How? Yes, you just to take amplitude and this is the location, that is x. Okay, this is the amplitude. And we draw a similar kind of plot. Yes, so yeah. Here now, can you tell me what is this guy? What is this guy? Now, if you draw this amplitude versus location plot, it will be something what she said. Okay, this this guy was representing period in the case of time, but when you have a location, this guy will represent the wavelength. When you have a amplitude versus location plot, and you get a sine wave like this, any wave like this. So, which was, if you had a time plot, it gives you a perfect example of why this is a period. Okay. But now if you do a amplitude versus location plot, the same quantity which gave you a period is nothing but the amplitude. I ask you to think about it. Okay. I ask you to think about it. Why it is the case. Why this guy is the amplitude. Sorry, this guy is the wavelength. But as usual, what is the amplitude in this case? Amplitude is the same. Amplitude is same in both the examples, whether it varies in time or space, the amplitude of the wave will always be this. But why? If you consider the amplitude versus time plot, this is period. But when you consider amplitude versus location plot, this guy is the wavelength. Okay. So maybe I can ask sometime later. Hmm? So think about it. Think about it, why it is the case. So before going into deep into wave, I just wanted to show what these quantities are really. Hmm? What is the frequency of a wave? Yeah, number of oscillations per second, isn't it? So if you see this guy, yes. So now suppose this is 1, this is 0 to 1, this is 0 to 1. Suppose, okay. Now you can see that in this plot, it did only half of the oscillation, but in this plot, it did already 3 oscillations, isn't it? So you can see why so we say that the frequency in the second plot on the right is more than that of the left plot. Okay. So here the frequency is like 3, but here the frequency is still half or 1. Okay. So you can see the number of oscillations here are more in that 1 second, but here the number of oscillations is just, maybe if I take this one also, it is just completed 1 oscillation. Okay, so this is the frequency. Frequency is just 1 by period, you can consider. Frequency is just 1 by period. So these are just basic concepts of what you call wave. Already you must have learnt in your basic physics and all these things. And these waves, we usually sample it. I tell you, you in real life, you will never get a continuous function like this given to you. No one will give you that take sin x. No, everyone will give you a data set. Okay, and if you plot those data set like these blue points, again, these are the data set. Then you will get a feeling that yes, this is sine plot. Okay, so this is something known as sampling. This is known as something known as sampling. So how many sample points you want to take in your wave case depends on you, like how much you collect your data. Fine. So this is just the basic understandings of the waves. Now we will make like I think an entry to the Fourier transform. Okay, so just hang in there. Yes, I forgot one more term also. So finally, till now we did not define how a wave looks like. Okay, we talked so much of waves, but we still did not define how a wave looks like. If you remember your bit of physics class, like maybe you can define the wave to be like say y equals to say a sine omega t plus phi, isn't it? How many of you remember this in your class 12th? How many of you did not see? How many of you are seeing this for first? Okay, that's good. So, so yes, this is just a wave, and this is the amplitude of the wave. This is the amplitude. What is this? Yes, this is the frequency of the wave. This is the phase of the wave. This is the phase of the wave. Okay, and here is the time factor, the time instance. So this is general expression of the wave. Okay, and this omega is related to the frequency. This is known as the angular frequency, and we say it is related to the frequency as 2 pi into the frequency f. Okay. These are just basic physics part, won't affect your understanding of discrete Fourier transform. But I just wanted to tell this before we begin. Okay, fine. So you know about now sampling rate, you know about angular frequency, you know about phase. I think we are good. So we'll move. Yes, I think we can make an entry to our Fourier transform. So yes, let us see. Like the wave you just saw here is quite easy. The wave you just saw here is quite easy, isn't it? Just by looking into the wave, you can find its period, and also you can find the amplitude of the wave. Also, you can find the like what else can you find? Like the wavelength of the wave. Hmm? Everything you can find. Why you can find? That's my question. Why you can find so easily? It's mainly because the wave is so simple. It's mainly because the wave is so simple. Okay, now I'll give you a wave and I'll ask you what is the period. Okay, ready? Take this example. Take this example of the wave. Okay, so you see on the y-axis is amplitude and time. So this is a wave. Now this is a complicated wave. Now can you tell me what is the period of the wave? What is the frequency? What is the amplitude of the wave? Is this wave complicated or simple? It's complicated. Yes. Now how for this wave you will know the amplitude, frequency or any other thing? See, this wave you are seeing it. I'm giving you, this is also a simple wave if you consider an example. But real life data, if you see, it is representing a very different wave, very hard to visualize. Okay. Now look into this wave and tell me like, how can we just by looking like previously to the sine wave, can you decide the amplitude, frequency and all those stuff? So therefore, like these complicated waves, we need some kind of technique to analyze. Okay, uh, previous characterizations are not enough. Previous characterizations are not enough to find the properties of these waves. Okay, any ideas you have so that you can tell? I'm open for 1 to 2 minutes. Any other ideas? Ah, in average, like yes, that's a good characteristic, but that we won't take here. Okay. Okay. So therefore, like the Fourier transform has to be used in these cases, and Fourier transform serves the purpose to study these kind of complicated wave. So this is a complicated wave. This is a complicated wave, and Fourier transform. Fourier transform helps us to understand these complicated waves. Okay, that's the duty of this. That's the job of the Fourier transform. Okay. So what you do with this, well, how it does it, first of all, how it does. So what Fourier transform does is, what is the input of a Fourier transform and what is the output of the Fourier transform? That should be our aim. Okay, that's all we need, right? What is the input of the Fourier transform? input to a Fourier transform is a complicated wave, just like you saw on your right hand side, just like a complicated wave here. And what is the output of that Fourier transform? It will be if you give Fourier transform a complicated wave, the Fourier transform will take that wave, and the output of the Fourier transform will be a summation. Like it will give you different important components of the wave. Okay, so that when you merge those waves together, you will get this original wave. Got the idea? Maybe I'll tell it in a good way. It decomposes any signal, like complicated signal, into a sum of fundamental sine and cosine waves. Okay, any wave you give, he will decompose the signal, the given input signal, into the like the sum of both sine and cosine waves. Okay, which will add and see that it is actually the first input wave. Why? Can you see that it has reduced your burden? Because initially you were not able to analyze the complicated wave. What you did, you gave Fourier transform, you applied Fourier transform, and then it decomposed that signal into simple sine and cosine waves. Okay, but can you analyze the sine and cosine waves? Yes, you just did in the previous page. Okay, so you can analyze sine and cosine waves, but you cannot analyze the complicated waves. So Fourier transform acted as a bridge. Okay, Fourier transform acted as a bridge. Hmm. Sum of fundamental sine and cosine waves, isn't it fine with you? Okay, fine. So yeah, so this part which I just mentioned you right now can be visually understood. You can visually understood this picture over here, right here. So what it does is, this is your input. This is your input you give. This is the input, the wave, complicated wave is your input. What Fourier transform does is it will decompose that signal into fundamental sine and cosine waves, which you see right here. So it has divided this complicated wave into the sum of the blue and the sine, three blue curves. Can you feel that these are sine components? These are sine components, isn't it? Okay, so this is the original wave you are getting, and you decomposed into a sum of these three sine waves. Okay, that is the job of Fourier transform. But there is something more interesting which you did not see here, Okay, but will it be easier to just say this thing like take this input wave and these are the output waves? It's not that easy. What is rather easy is, how about you pick a characteristic of each of those decomposed wave and plot it. Okay, so what here it is doing is, you see, this is 1, this is 2, this is 3. This guy has been decomposed into 3 waves, of which are looking like sine waves. Okay, and what this guy does is it records the frequency of those 3 waves. Okay, so you can see that previously your wave was in time domain. Okay, communicate this to him. Huh? Maybe Mr. Jubin Babu can put some knowledge there. Okay, so this is the wave with the time domain, right? What you do, what Fourier transform does, listen to this very carefully. This is the coconut oil of the coconut. Okay, yes, so what it does is, the wave exists in the time domain, and you apply the Fourier transform, then the wave gets converted into frequency domain. From time domain, it goes to frequency domain under the application of Fourier transform. Understood? So this was your time domain. What you did, you went to frequency domain. Just by applying the Fourier transform. Okay, this is the job of Fourier transform. You take the data in time domain and you apply Fourier transform. then it will translate into the frequency domain. So you can see, and you should ask me the question, what is the frequency domain in this case? It is the frequency of the yeah, it's the frequency of the wave, but frequency of, there's something more than that you can tell. No, no. Frequency of the, right, say more generally. Frequency of the decomposed waves. See, this blue guy you see, how many blue curves you see? 3. So this red curve has been decomposed into the sum of these 3 blue curves. Okay, if you plot those 3 blue curves together, it will give you this red curve. That is the idea of Fourier transform. Okay, now how you can visualize these 3 curves separately? That's my question. What you can do, you can plot a characteristic of those 3 decomposed waves. You can plot period, you can plot anything, like, but frequency is the most desired one. Frequency can give you all the aspect how the wave looks like. Frequency is one such important parameter. Okay, so therefore what you do, you plot the frequency of each individual wave. So how many lines you see, these are the frequencies. This is the frequency, and this is the amplitude here. You can see this guy tall, whose amplitude is more, 1 2 3 out of. And do you see this blue line is taller there? It's the height is more, isn't it? Yes. And the middle plot, even it is bit less than the first. So, but it is in the middle of 1 and 3. And the third wave has the least amplitude. You can see that. Is it okay? Are you understanding the logic behind this? What is happening? So what we learned here, Fourier transform. Fourier transform. What is the job of Fourier transform here so far? What is the job of Fourier transform? Can anyone tell me from this side? Maybe the last 2 benches. First point, what the Fourier transform does. Hmm? Yes. So first, as he told, like first job of Fourier transform is to decompose the input signal into the sum of fundamental sine and cosine waves. That was clear, isn't it? That was clear. Hmm? Then what else? Yes. Fourier transform, like if you give for what the Fourier transform does, no, sorry. What Fourier transform does is it takes the time domain signal, the signal in time domain signal, okay, and converts it into the frequency domain signal. Okay, so that's the job of Fourier transform, and you can see that here it is time domain and here it is frequency domain. Okay, so this is the job of Fourier transform. I hope it was clear. Now something is going to be a bit messy. So I gave you as much visualization possible. Now it is going to be a bit messy, but I think you can digest. Okay. So, but don't worry about it. Like, it is just the formulation. You just have to understand the concept. Don't think how this formula came up. Do I need to memorize this formula? No. Just see what I'm writing and understand what is going on. That's it is needed. Okay. So, yeah. Yeah. Do you want break or something? To 3:30, 2 to 3:15 it will. So 1 hour 15 minutes. maybe break. After that, so I will tell you what we will see after the break. I will clearly define what is discrete Fourier transform mathematically. We will discuss what it is, and then we'll see some Python codes and see discrete Fourier transform in action, like what kind of like commands you can apply in Python. If you give a data set, it will give you the frequency domain components. Okay, can you understand? Can you understand? See, just by looking into this data set, just by looking into this red plot, you are not able to get any information out. Can you understand what is the frequency of this plot? Anything like that? No. So you need some kind of technique to understand this. Therefore, we introduced Fourier transform. What it does, it decomposes the signal into. I will ask you one question. When the shopkeeper tells you, you buy a lot of stuff from the shopkeeper, right? Like 1 kg potato, 1 kg rice, 1 kg chicken, 1 kg something for biryani. Yes. So when you cook it, okay, when you take all that and you ask what is the amount, then he tells you certain amount. What you do in your brain to see whether it is correct or not. Suppose it tells you 337 rupees, okay, 337. Then suddenly 337 brain is not able to process. What you do it, yeah, let us do 300, then 30, then 7, isn't it? Isn't it? That's the best example you can see for yourself. Okay. Yeah, I think that is a good example. Or since it was biryani day today, so I'll give you one example related to biryani. If the guy gives you the biryani in the plate, right? What you do? You separate the chicken out, isn't it? The chicken are the most important elements. So you have to take the important aspects from the signal. Hmm? Any other ideas you are having? Say like we are separating chicken. Important elements. I just say not for everybody. Oh, okay. For paneer, like those are vegetarian. The pounded paneer curry. Um, Now it is even more fun. Oh, okay, so let us start. So we were discussing like Fourier transform, and we discussed how it converts the amplitude signal to frequency signal. Okay. So what is DFT? What is DFT? So DFT, let us discuss this mathematically. What is DFT? Okay. So it is not that straightforward. Not that straightforward. So the expression I'm writing now, just now. Okay. So what DFT does is it will transform a sequence of evenly spaced signals, okay, to obtain the time domain signal. So just see this expression over here. So you have this xk. Xk is nothing but the DFT. Xk is nothing but the DFT. It is equal to sum of some components, and we are going to see what are those components. I will tell you each of these variables, what each of these variables mean. Okay, so here, like as you see some different variables. I'm going to say what each of this means. Capital N is the number of samples. Okay, the number of samples. Capital N is the number of sample. Small n is the current sample that you are focusing right now. Okay, so n is small n equal to 0 to capital N minus 1, and small n, you can see n is the total number of samples. So it is going from 0 to n minus 1. How many samples you are taking from, if you are taking from 0 to n minus 1? N samples. Okay, so that is in line with whatever you have taken. Small n is the current sample you are concentrating right now. So you can see this is the index right here, n. Okay, fine. Then you have something known as a K. What is this K? So K is the current frequency, because you are taking the current sample, it is the frequency of that current sample. Therefore, it is known as the current frequency. Okay. So actually, this is 2 pi f. I hope you remember omega equals to 2 pi f. And instead of f, we are just writing K. Okay, so you can see this term over here. What is this term? Fine. Okay. What is xn? X sub n. X sub n is the sign value. Okay, is the sign value of sample n. Okay, of the current sample. That means of sample n means of the current sample. Okay. So what is xk? X capital Xk. As I told you, it's the DFT. That's the output you read. So it's a discrete Fourier transform, what you expected. But DFT of what? DFT, which includes DFT. This includes the information. It includes information about what kind of information it includes. It includes information about magnitude is nothing but amplitude. Okay, amplitude, the phase it has. Okay, and also maybe the frequencies. Okay, all the information is packaged in this capital X sub k variable. Okay, and that's the DFT. Okay, so DFT is a frequency domain interpretation of the original input sequence. Are you able to digest this word? So capital Xk is the discrete Fourier transform. Okay, and it includes all the information of that signal, input signal. So you know, at least you know why there is a summation sign, isn't it? Do you know at least why there is a summation sign? Yeah. So do you know at least why there is a summation sign? I was asking you. Because you know, if you give an input signal to DFT or any Fourier transform, what it does, it will decompose that signal into different signals of sine or cosine form, isn't it? Of sine or cosine form, and add them up, isn't it? Therefore, you see the summation. At least that you have a basic intuition why this is there. Okay. But it's fine. It's fine. Let me just explain this. So any wave, you can express it in terms of cos and sine. And yes, this complex part is taken. No, don't worry about this complex part. Okay, we will be mostly focused on the real, but this is the interpretation, like how it is. Don't think that yeah, we are getting complex numbers. How in real data we are dealing with complex numbers. Don't think all these things. Okay, you will see how the magic happens when we actually discuss the Python code. Fine. So anyway, so why I tell these guys to you, amplitude and phase. So what can be the amplitude? Anyone? Amplitude. See, you are summing up, right? You are summing up capital N number of samples, isn't it? Agreed with me? Yeah, you're taking a summation from 0 to n minus 1. So you are taking n samples. Okay, and each sample has its own amplitude. Okay, so if I sum up those amplitudes, will it be correct? If I only sum up the amplitude and say this is the final amplitude? No, I have to divide by the total number of samples to say it to be an average amplitude of the whole sample. Okay, So therefore, amplitude of xk, amplitude of maybe your signal of DFT signal is this guy. Okay. So this is just a basic understanding, like mod xk. Okay, xk, why we have taken mod? Any ideas? Do you remember in the sine wave, you had a positive up, but you had a negative down also. The negative down has a negative value. But actually, if you consider the amplitude, you have to take the mod. Otherwise, all them, even though the amplitude is pop like a value non-zero, but due to this plus and minus, they will cancel out when you add them up. And that is not the true factor, right? So you have to take the modulus, isn't it? Okay. And what is the phase? Phase of the final signal. So it is tan inverse of y by x. I think you know this formula, theta equals to tan inverse of y by x, isn't it? So it's just the same. It's just the same. Tan inverse of xk. Xk has a real part and an imaginary part, isn't it? Xk has a real part and an imaginary part. So how you will find the like the angle? So think of a complex number. Think of a complex number. How the complex number lies? Here, suppose z cos theta plus I sin theta. How it is defined? This complex number depends on theta. With respect to what? With respect to this base. What angle it makes theta? Isn't it? Then, if it makes an angle theta, this guy, this point here z, is referred to as cos theta plus I sin theta, right? And what should be the slope? Slope should be tan theta. Tan theta equals to, actually you are saying tan theta, but you see it is falling very nicely. It is just the imaginary component divided by the real component, isn't it? What is the imaginary component here? What is this real one? Cos theta. You see, tan theta equals to sin theta by cos theta. Indirectly also you derived that tan theta equal to sin theta by cos theta also. If you are confused, you can just think along these lines. So you got to know that the slope or the phase, you say, the angle you want. So if you want the angle, what you do? Tan inverse of the imaginary part divided by the real part, isn't it? So can we apply this guy to here? Can we apply this concept? Can we carry over this concept? So phase equals to tan inverse of the imaginary component divided by the real component. So what's the imaginary component here? Yes, that's the remaining, like, yes. So you will get to see what you are getting. Sine of 2 pi k n divided by n divided by cos, right? And you're getting tan, right? Inside you are getting tan again. So those tan and tan inverse, you can cancel it off. So what you're getting finally? Hmm? Yes, that's it. But is it correct? That's what I'm thinking. Okay, so you got a basic idea where the angle actually lies. You can see we considered all the real parts and everything, but all the angle, the phase lies in this part of, like, whatever argument you have inside sine or cos will play the role of the angle or the phase. Okay. Anyway, so now I will show you, we will take that same image we have taken here. We will consider this image, sorry, this signal, this complicated signal, and I will show you that this signal is made up of three signals, isn't it? We discussed these are made up of three signals, right? I will show this in Python that they are actually made up of three different signals. Okay. Yeah. So I think I have that. Yes. So see this question here. Generate three sine waves. Are you able to read the question? Generate three sine waves with three different frequencies. That is, generate three sine waves with frequencies 1, 4, and 7. Okay, 1, 4, and 7 hertz. Fine. Frequency unit is hertz. With amplitudes 3, 1, 0.5. Okay. And phases being all 0. And add these three sine waves together and you have a sampling rate of 100 hertz. Okay. Fine. So let us see. So we have to create these three signals, and after you add one signal, add into an array, produce the next signal, add to the same array, third signal, add to the same array. So that final array consists of three sums. Isn't it the first sum, second sum, and the third sum? That's the exact logic of this code. Okay. So yeah. So you can see like the sampling rate, I told you the sampling rate is nothing but the amount, the intensity or the density of the points you need to have. You remember the blue dots in my sine curve. So that's all it is inside this sampling rate. Okay. So you can see sampling rate I have considered 100. We will take different sampling rate and see what happens. If you take naturally, if you take more number of sampling points, your code will be running for a longer time. Definitely. Okay. So sampling rate and sampling interval, up to what interval you want the wave to be. Okay, so that is here just defined by TS variable 1 by SR. SR is nothing but sampling rate. It's fine. If you are not clear, it's okay. Okay, here just think that you are running from time t equal to 0 to time t equals to 1. And what is the link space? What is the step size? No, it is not 1. It is TS. No, it is 1 by sampling rate. So if the number of points are 100, so it should be 1 by 100, 0.01. So you have to go from time t equal to 0 to time t equals to 1 with the step of 0.01. Okay. So as per the question, first frequency is 1 hertz, next frequency is 4, third is 7. Okay, see this equation here. I did not take the one. Oh, I think this is the amplitudes 3, 1, and 0.5. Can you see that the amplitudes here is 3, then 1 is multiplied here, 0.5 is multiplied here. Is it clear? No. Okay. So frequency is 1, fine. Let us see first this line. See my cursor. Are you able to see the cursor? X equals to 3 into sine 2 pi ft. So what is being written there in the code? What is being written there is 3 sine 2 pi ft. Okay. Can you decode this? Then what you do? Then what are you doing? Do you remember why we wrote like this? A sine omega t plus phi, isn't it? That is a general form of the wave. And in the question, it is given to you that the phase is 0. Phase is 0 means phi equal to 0. So only omega t term you are seeing. This is omega, isn't it? Omega t. So plus 0, that is phi. And what is the amplitude here? 3. Same. So done. So this is done. Then what you are saying, the frequency is 4. Okay. Because you are saying 4 hertz here. 4 hertz here. Okay. And you are doing that. But for the 4 hertz, the amplitude is 1. So you are multiplying 1 times sine 2 pi ft. Okay. And f is 4 here. Okay. And similarly, you do with the last waves, that is 7. And you keep on adding. That is the help of this x plus equal to. X plus equal to. You previously had that thing and you are now adding that new thing to the previous thing also. Okay. Fine. Like that, you add these signals over here. Then finally, x is the sum of all the signals. Agreed? Agreed or not? Yes, x is, how many of you don't agree? X is the sum of these three signals, I'm saying. Agreed, right? How many of you don't agree? I'm just asking. How many of you don't agree? What is the difficulty? I don't know. So you can see this wave here. Okay. So the amplitude versus what? Time. What is the x-axis? Time. Because you're, yeah, I did not write, but you should know it is time, because in the code I told it is varying from 0 to 1. Okay. So amplitude versus time. And you saw just I added these three components and it is giving you this graph. And Fourier transform exactly does that. Okay. When you apply a signal, complicated signal like this, it will give you these three distinct formulas of the waves. Okay. Fine. So I think this is a good example so that you can understand what is going on. Okay. So let us apply the function dft which you just saw right now. So did you see the function I just applied? I wrote here. So dft is exactly this. Okay, dft is exactly this guy. Okay, let us apply this in Python. Let us apply this in Python. Okay, where the input signal small xn is the wave just we saw before. Okay. So yeah, yeah. Yes. So you can see, yeah, this is the function. Write a function dftx, okay, which takes in one argument, okay, x, that is a real valued, one-dimensional real valued signal. Consider this importantly. I'm saying one-dimensional real valued signal. You should ask me, what about a two-dimensional real valued signal? What can a two-dimensional signal mean? Can you give examples? Image. Image. That will come soon. Okay. So you will see why DFT is helpful in denoising the image. One-dimensional signal can also be audio signals. Okay, you will learn why DFT can also denoise audio signals. If you want to denoise any data, DFT can be used. You will see why. You will see why we can take the advantage of breaking down one complete signal into multiple signals, sum of multiple signals. Anyway, so this is the dftx. The function will calculate the dft of the signal and return the dft values. Apply this function to the signal we generated above and plot the result. Okay. We'll see how dft is being applied, but before that, can you agree to yourself that this is the same term we saw in your notebook right now? Isn't it? Is this the same term you saw in your notebooks? Yes? Okay. Hmm? Fine. So we are defining a function dft of x. It will take small x as an input, and this will be the capital X will be an output. Okay. It is nothing but xk. Capital X you are seeing is the same guy. Capital X you are seeing is same as this. Okay. And yeah, I think small x, small x you are seeing. You are just doing this e to the power x. Fine till now. So so what this function does, if you give small x, it will compute the DFT. It will compute the DFT. DFT is just that exponential term I just defined in the notebook. Fine. As usual, like total time is the number of samples divided by the sampling rate. Okay. Don't worry about these terms. It will come to you. But I am just plotting that. I'm just plotting that. Okay, frequency versus the absolute value of x. And you see something remarkable here. Something remarkable. Something very nice. Okay, what does this tell us? Can you think? What does this tell us? We are considering that same signal. Don't worry about what kind of signal it is. Just the same signal, the complicated wave. The DFT of the complicated wave looks like this. This is the frequency domain plot. This is the frequency domain. Why I'm saying frequency domain? It is not time domain. This was time domain. This was time domain. The x-axis is the time here. But this is frequency domain. Why? Because x-axis is the frequency. You saw we are still on our track. I told you what Fourier transform does. It takes the amplitude signal, converts to frequency time response signal. Okay. So this is the output of DFT, but how can we interpret this output? How can we interpret this out? Anyone? Remind yourself of this plot. Remind yourself of this plot. What this plot does, this plot does. Okay, can you tell? So this plot shows us that if you apply the Fourier transform, it converts time domain to frequency domain, and also it tells that the red signal FFT, what it does, it decomposes into 1, 2, and 3 different signals. Okay, and yes, what we say, like you take one important characteristic of each of those signals, and that is the frequency. Okay, so this guy on the top, you see, this is one frequency, this is the second, this is the third frequency. Okay, and we just record the height is the amplitude also. So this is giving you, so you can understand that why you are seeing now 3 bars, isn't it? I hope it is clear, isn't it? You are seeing these 3 bars. Yes, but something is worrying us here. Something is very worrying here. You already got these 3, okay? And you, why are you seeing again these 3 here? And you can feel that they are of exactly the mirror image. If you see the middle plot around 50, around 50, around, so you have 0 to 100, isn't it? 0 to 100. Think of this as a paper. I printed it out. Think of this as a paper. What I do is at 50, at frequency 50, I just fold it up. Yes, at frequency 50, I just fold it up. Exactly merge. Yes. So this is completely symmetric. And this is a very striking result in FFT. Okay, like not FFT, sorry, DFT. So DFT, when you apply DFT to a signal, the signal will give you what are the most important components in that signal, in that complicated signal. So you know that there are 3 different signals within the complicated signal which are important. Others are not important. Okay. And these 3 signals, if you merge them together, will give you the final signal. Now suppose you want to remove the high intensity amplitude from the signal, from the complicated signal. What you do? What you do? You just eliminate this guy. You just eliminate. We took 3 wave expressions, 3 wave expressions, right? Remove the wave expression from your summation, which contributes to this highest amplitude. Which one was that? Can you tell which one was contributing to high amplitude? No, huh? 3 is their amplitude. So amplitude 3 is there, no? That is the highest amplitude. That amplitude is written here. A sine omega t. So 3 sine omega t. So this if you remove, then shall we remove? Uh, this one we should remove. So uh, yeah, you can see that um, yes, now everything like the whole wave structure changed. But anyway, like you if you don't want that high amplitude signal in your plot, this is removed. What was the amplitude? 3. In this signal, do you see in this signal which is plotted here, amplitude is going to 3. The final amplitude is not going to 3. Okay, so you see how important it is. Okay, you see how important it is. If you have an input signal which is giving you loud noises, heavy amplitude noise, so what you do, apply the Fourier transform of the noisy data, then the output will be in the frequency domain peaks, which are the important peaks. Then you remove that highest peak, then the noise in your audio will decrease. That's the idea. Okay, we'll see those applications just now. Let us change it because I want to consider the same example, because this X is used throughout this collab. plus. Sounds good, right? Correct me if I'm wrong. Fine. Okay. Same signal, no? Is the same signal, right? Yeah. And this is the frequency response you are seeing, right? Now, researchers thought that discrete Fourier transform is good enough, that it is giving you three peaks and giving you a lot of information, but you are doing twice more computational work than needed. Because see, here you already got these three peaks, here you already got these three peaks, and you are again seeing those peaks here, which is not needed, which is not needed. So, therefore, something came up known as fast Fourier transform. Something which is came up that is fast Fourier transform, which can avoid this. Okay, which can avoid this. What fast Fourier transform said? Fast Fourier transform said you don't need to compute for the whole time interval 0 to 1. Instead, you compute from 0 to half of the time interval, like the frequency domain. You go from 0 to half of the frequency domain being considered. That's the example of Fourier transform, fast Fourier transform, FFT. So even if you learn DFT, discrete Fourier transform, to make it more efficient and faster, you have to learn FFT, fast Fourier transform. Okay. So I hope you're getting some ideas, and these are not just too abstract. What is the most important point here? The most important point you learned from this code is the output of DFT is always symmetric, which you just saw right now, isn't it? Isn't it symmetric? Yes. Therefore, DFT is slow. Because DFT is symmetric, it is slow. Okay. So let me write it down. Um, okay. So the output of DFT is symmetric. The output of DFT is symmetric at half of the sampling rate. At half of the sampling rate, which is just in the frequency domain. So this is just a proper way of writing it. But you know, if we were having 0 to 100, and at 50, you can see that it is a copy of each other, is a symmetry. So it is symmetric at half of the sampling rate. And this half of the sampling rate is something very popular. And someone who saw actually this one, who first saw this, we'll write the name of the scientist. So uh, if you can spell it out. Okay. So yeah. So NY, okay. Quist, okay. Quist, we can say. So this is something known as Quist frequency. So this is special frequency, okay. That something at half happens. It is symmetric at the half of the sampling rate of the frequency, and at that it is just a mirror image. Okay, so now for what fast Fourier transform does, you enter only the data from 0 to least frequency. That's what. You don't need to go to the whole frequency. Just give the data of only the half. That's how you reduce the complexity from 1 to half. If it was taking 50 seconds, it will drastically reduce. I'll show you some computational time. Okay? It is also something known as a folding frequency. Why this is known as a folding frequency? Because I just told you, think of it as a paper and fold it. It will exactly merge on top of each other. Okay. So that is fine. Okay. So after you apply DFT, discrete Fourier transform to a signal, you can also apply inverse of that DFT, okay, to the same signal, to the broken signals, to go back to the previous signal. Okay. Are you getting that why I am talking about inverse now? See, just think, I think these terms are a bit confusing because the frequency, the amplitude, wavelength, and number of samples, sampling rate, these are too many parameters to consider. But just get an idea, of this, that if you have a function f of x, okay, f of x is important. Why? You put that x inside f and it computes f of x. But at the same time, you also need to know what is f inverse of x. Okay, you also need to know what f inverse of x, isn't it? So similarly, we want to learn inverse of DFT. So I will write what was DFT, then I will tell you how it is related to DFT. Can you tell me from your notebooks, like, what is DFT? We had, okay, we had xk. Yes, what is xk? Xk is equals to, yes, yeah, so yeah, so xk is nothing but the sum, right? So you have n number of samples, capital N number of samples, n minus 1. So it is going from small n equals to 0 to capital N minus 1. And you have this xn, e to the power minus I 2 pi kn over n. Check, is it the same or any notational difference? No notation change, no? Yes. Now, if this is DFT, can you tell me what should inverse of DFT look like? So you are getting the output as capital Xk when you're giving this as input, small xn. Now, if you want to compute inverse DFT, what should be the output? The output should be xn, small xn, and inside that there should be capital Xk. Isn't it? So how you can define it? Any ideas? Hmm? Any ideas? It will look a bit similar, but not exactly similar. That's the issue. Okay, that's the issue. But anyway, these are just for you to know. Nothing hard to remember anything. You don't need to remember all this stuff. Just need to remember the concept. Know the concept, like what DFT does. What is the use of inverse DFT? Okay, like that. Hmm? So if you just see, like, I'll just write it down. Okay, just hang on.